Hello, my name is Konstantin Morozov, and I'd like to present you materials of paper on determining the state of the processors of a multiprocessor system during its testing, written by Alexey Romankevich, Konstantin Morozov, and Vitaly Romankevich from National Technical University of Ukraine, Igor Sikorsky, Kyiv Polytechnic Institute, for the third international workshop on intelligent information technologies and systems of information security, Intellicis 2022. Let's see the plan of the presentation. First, the problem of testing of multiprocessor system will be described. One of possible solutions is mutual testing of processors of the system, and it will be described in more details. Then the previously obtained results in this area are provided. After it, there is a detailed description of proposed formal method for determining the state of the system is presented. The problem of evaluation of test completeness is described then. To solve this problem, the auxiliary statements are formulated and proven in the paper. Based on these statements, the criteria for selecting the value of M, the maximum number of failed processors, are proposed. Then several examples are considered, and finally the conclusions are presented. Testing of a multiprocessor system is a determination of the state, operable, faulty of each of its processors. The obtained information about the state of the processors allows the system to use the available reserves for reconfiguring the system to restore its performance. Evaluation of the state of the processor is done by means of execution of a set of tests and comparison of the results with the reference values. There are several options how processor testing can be done. The first option is it can be done with a separate specialized node. The implementation of this approach is simpler. However, it should be noted that this node may also fail. And this option is good enough for system testing at production and service stages. However, it's maybe not so good for operation stage. Another option is when the state of the system, so states of each its processor, can be estimated as a result of their mutual testing. So there are pairs of processors, testing and tested processors. In this case, there is no separate nodes, and it may be good for operation stage of the system. However, implementation of this approach may be much more complicated. In particular, the task of determining the state of each processor from the results of mutual tests. The solution of this problem is proposed in this work. We assume that the testing is conducted according to the preparatory Metz chain model. According to this model, the result of testing of the processor with an operable processor will be 0 if the processor is operable, and it will be 1 if the processor is faulty. However, from the other side, if testing processor is faulty, the result can be either 0 or 1, regardless of the state of processors under test. So the test results of faulty processor cannot be trusted. This also assumes that links between the processors are operable because the probability of their failure is relatively low. It also should be noted that in general case, the topology of interprocessor connections may be arbitrary. It is not always possible to organize testing of each processor by any other processor. Capabilities of mutual testing of processors can be represented as a directed graph, as you can see on the figure. Each vertex of this graph corresponds to a certain processor, and the presence of an arc between the vertices means the possibility of conducting the corresponding test. This graph actually reflects the capabilities of the system in terms of diagnostics. It also should be noted that for any multiprocessor system, t-diagnosability takes place. A system is t-diagnosable if knowing the results of mutual testing of processors, it is possible to establish the states of all its processors in case of failure no more than t of any of them. Here we assume that the processor at the same time can be either tested or tested. Let's briefly review previously obtained results. So we should note that minimizing the number of tests carried out is an important task. Because each test takes some productivity of processor, some processing time. There is an algorithm that allows to determine the state of the system by conducting no more than n plus 2p test checks, where n is the number of processors in the system and p is the number of actually faulty processors. But the necessary condition is the completeness of the graph described above. The theoretical limit of the value t is also determined, and it is shown that it always possible to determine the state of all processors in the system if the allowable number of faulty processors does not exceed the value n-1 divided by 2, where n is the number of processors in the system. Also for the case of complete graph. It is also shown that this is almost always possible with a larger number of faults. However, unfortunately, real structures do not always correspond to a complete graph. So in this paper, we will deal with any possible structure of graph. The proposed in this paper formal method is acceptable for arbitrary structure of the graph. And let's assume that the diagnosed system which contains n processors. Let's assume the m and let's assign to each processor some boolean variable xi, where I is from 1, 2, and to the value n, where n is the number of processors. And this variable takes the value 1 if the processor is operable and 0 if it is faulty. Let w and f be sets of variables corresponding to actually operable and faulty processors. And in this case, the following equality will be fair. You can see it here. Here you can see that the variables corresponding to faulty processors are given with inversions. That is correct because their values are equal to 0. So when we invert them, then we will get 1. And then this equality will be correct. Let's build a table of values of the results of testing processor G by the processor I, depending on their states, in accordance with the preparator method chain model. It is this table. You can see when testing processor is faulty, then we can get any result that is described with asterisk symbol. And we can see the test result 0 can be obtained only in 2 cases, when both processors are operable or the testing processor is faulty. And the test result 1 can be obtained also only in 2 cases, when tested processor is operable and tested processor is faulty, or the testing processor is faulty. So when we write the corresponding, so we can write the corresponding equalities, which are presented also in table. And these equalities can be minimized, as you can see. So let's move on. Let's assume that after carrying out k-1 test checks, an equality of the form pk-1 that depends on some variables x of xi is obtained, and it's equal to 1, as we see. Now it's not no matter what is the form of this equality, but we will on the next slide we will define it. So now let's assume that case test consists of testing of J's processor by the i's processor. So processor number J tested by processor number I. And the result of this test is the value of Rk. It can be 1 or 0, depending on result of test. And let's build an expression R capital, which depends on variables xy and xj. And its form will be based on value of Rk. So it can be either this form or this form. So as you can see, this expression is built according to equalities presented on previous page. And let's build an expression vk as it is shown. So it depends on previous expression and current expression that corresponds to current test. It is easy to see that Rk, R capital K, this expression is always equal to 1. If we build it with this form. Therefore, it's true that vk is also equal to 1, because previous expression is equal to 1 and Rk is equal to 1, so the conjunction will be also equal to 1. So let's move on. So now let's take the initial expression v0, which is equal to 1. It's just 1. It's just not an expression, it's just a constant 1. After n tests, the following expression will be obtained. Vn is a conjunction of expressions Ri's, which are built as it's shown on results of appropriate test case. As it was shown earlier, the following equality holds: Vn equal to 1. We started from constant 1, so we can omit it here, and then we are doing procedures that is described on previous slide, and then we can obtain Vn. So now let's transform this expression to perfect disjunctive normal form, PDNF, which is the disjunction of elementary conjunctions, which are constituents of 1. So these are elementary conjunctions, constituents of 1. So this equality takes the form where disjunctions of elementary conjunctions are equal to 1. As it was said, each of these expressions Ci is a constituent of 1, the elementary conjunction, containing all the variables xy. And obviously that exactly one of these constituents will be equal to 1, really equal to 1. Let's call it CR, and this constituent will correspond to the real state of the system. Only this constituent corresponds to real state of the system, as we as we can see on previous slides. We built this constituent, and it will be equal to 1, and other constituents automatically cannot be equal to 1, because at least one of variables will be inversed and will give 0. Let's recall that the system is only M diagnosable, and therefore it is possible to determine the state only if no more than M processors have failed in it. And let's assume that this is true. So the number of faulty processors is actually no more than M. In this case, any conjunct containing more than M inversions will be equal to 0. So we can exclude from all of them which contain more than M inversions at any of the steps. Obviously, CR will contain no more than M inversions because it corresponds to real state where no more than M processors are faulty. So this conjunct will not be excluded. In the process of transformations, any conjunction of containing more than M inversions can be excluded, and it can be shown that the number of inversions cannot be reduced on these transformations. As a result of the transformations, equality can take one of three forms. The first one is exactly one of the constituents of one remains. The second one is when more than one constituent of one left. And the third one is when all constituents of one are excluded. Each of these forms can be interpreted as follows. In first case, the real state of system can be unambiguously determined from CR that is equal to this left CI constituent, and the processors corresponding to the variables included in the constituent without inversions are operable, and the processors corresponding to the variables included in the constituent with inversions are faulty. So this is the best case. In second case, the state of the system cannot be uniquely determined. However, the CR, so real state corresponding to real state, is among constituent CI. Additional tests are required to unambiguously determine the state of the system. If all tests have been carried out, the system is not M diagnosable, and sometimes it's possible to determine the state of some processors. Not always, but some processors, not all processors, but by some processors, maybe state of some processors may be determined in this case. And in the third case, the third case means that more than M processors are actually failed in the system. As you can see, to apply the method under consideration, it is necessary to set the maximum allowable number of faulty processors, M. This value depends on organization of the system, the capabilities of mutual testing of its processors, and as it was shown above, the capabilities of mutual testing of system processors can be represented in the form of directed graph. But now we are interested how to find this value of some given structure of graph. In the paper, the following auxiliary statements are formulated and proven. Let's assume that system contains n processors and corresponds to graph G. And when no more than m arbitrary processors fail as a result of a certain set of tests, it is possible to unambiguously determine the state of each of the processors. The following statements are formulated and proved. If for some group of n processors, it is possible to establish the state of each of them by conducting mutual test checks between the processors included only in this group. When no more than any m of them fail, then m is less than half of their number. So m is less than n divided by 2. According to the second one, the statement is that according to the proposed method, the reliable state of the system in case of failure of no more than m of its arbitrary processors with a given set of tests corresponded to diagnostic graph G can be established if and only if for any set F of vertices of graph G having power k exists t vertices of the graph G which are not contained in set F, such that from each of them there is an arc in at least one of the vertices from the set F. And there is a constraint for T presented on slide. So it's enough difficult formulation. And third statement is that fulfillment of condition of statement 1 for set containing all processors of the system. So when M is less than half of all processors number is sufficient to satisfy the condition of statement 2 for the set F containing all vertices of the graph G. And the fourth statement is that condition of statement 2 is always satisfied for sets of vertices with power k that is greater than double value of M. So these statements are formulated and proven in paper and are used for building criteria for selecting the value of M, the maximum number of failed processors. And this criteria is that the value of M, the maximum number of failed processors can be selected by checking all possible sets of vertices in the graph G for compliance with the conditions of statement 2. And we can find this value of M, the maximum possible value of for which all conditions of statement 2 will be will comply. Then this value will be the value of M. However, this criteria is not so useful, and there are also more simple criteria for choosing this value. The first one, the value of M must be less than half of number of system processors. So this filter can be used to find some bound of value of M. The second one criteria is another one, give us another one bound. So in graph G, the number of arcs entering each of the vertices must be not less than M. So we can find some vertex which has minimal number of incoming arcs, and the value of M will be not greater than this value. And the third one criteria is that for each set F of vertices of the graph G with power k, where k is between 2 and double value of M, there must be a T which with appropriate constraint presented on slide, vertices on contained in F, and from which arcs entering some vertices from the set F emanate. So this is criteria. We should here we should enumerate all possible sets, but there is some constraints for power of these sets of vertices. So these criteria can be used for to find the appropriate value of M. Now let's move to several examples. Here we have the system consisting of 5 processors, and let's show that here M is equal to 2. We can note that the graph is symmetrical and it significantly reduces search. We can see that criterion 1 is satisfied because 2 is less than half the number of processors, that is 5. Criterion 2 is also satisfied because for any of the vertices of the graph, there are exactly 2 vertices from which arcs emanate to the given one. Now let's check the fulfillment of criterion 3. Consider all possible combinations or combinations of vertices for k laying between 2 and 4. For different pairs of vertices, k is equal to 2. This corresponds to figure A and B. We can see that t is equal to 2 or equal to 3, and it corresponds to criterion 3. For triplets of vertices, k is equal to 3. It's figure C and D. We can see that t is equal to 2, and it also corresponds. And for different quadruplets of vertices, k is equal to 4, figure E, t is equal to 1, and it also corresponds to criterion. So conditions of criterion 3 are satisfied. And the value of m is really equal to 2. We can see it is maximal possible value of this system. For example, 2, the system consists of processors arranged in the matrix A multiplied B, where A and B are greater than 3, not less than 3. Let's show that m is equal to 4. So criterion 1 is satisfied because n is equal to a times b, that is not less than 9 for case of a, and b are not less than 3. So m is equal to 4 will be anyway less than half of number of n, number n. Criterion 2 is also satisfied because for any vertex of graph exists exactly 4 incoming arcs, as we can see on the picture. Next, having considered all possible groups of vertices of 2, 3, 4, and up to 8 vertices, we can make sure that criterion 3 is also satisfied. But on the slide, there are depicted only some possible groups to simplify. However, we should enumerate maybe more possible combinations. So the value of m is really equal to 4. And for third example, here the system also consists of 5 processors, but the graph is not symmetric, as we can see. Let's show that m is also equal to 2. So criterion 1 is satisfied because 2 is less than half of number of processors, that is 5. But to check the fulfillment of criterion 2, we can build a table. Here, for each vertex of the graph, we determine how much incoming arcs are presented. We can see that this value is equal to 2 for any vertex, so criterion 2 is satisfied. To check the fulfillment of criterion 3, we also can build a table. Here we enumerate each possible set of vertices with power between 2 and 4. We find number of vertices being out of this set and having arc from self to at least one of vertices of this set. So we check these values with in equation of criterion 3. And we can see that for each set of the condition of criterion 3 are satisfied. So we ensured that m is really equal to 2. Now let's move to conclusion. On development of self-testing multiprocessor system, the development of a test, a set of test checks, is a separate important task. One of the important requirements for such a test is its completeness, a guarantee of determining the state of processors. It is assumed that there are certain restrictions, among which, in particular, sets of permissible processor faults can be distinguished. In practice, these are the permissible number of faulty processors. It is important to be able to check the completeness of the test for given constraints. For the previously proposed formal method for determining the state of the system during its testing, there are formulated criteria that allows determining the maximum number of faults that allows its effective use. In general case, checking the conditions of the criteria is associated with the enumeration and evaluation of all possible subsets of graph vertices. But in case of symmetric and homogeneous structures, enumeration can be significantly reduced. Thank you for your attention.